I'm Doug Simons, the director of the University of Hawaiʻi Institute for Astronomy. Based here in Hilo, the IFA is actually one of the larger university astronomy programs in the world. We have facilities here on Hawaiʻi Island, Maui, at the we call ATRC, the Astronomy Technology Research Center, and the hub of it all historically has been at UH Manoa over in Honolulu. So between these three facilities, the laboratories, the shops, the telescopes on Mauna Kea and Haleakala on Maui, it's a very extensive distributed astronomy program that we have across the islands here. I have been with Hawaii astronomy for most of my life. I got my undergraduate degree at Caltech and then came here for my graduate work and kind of never left after I got my Ph.D. My first job was a research astronomer at Canada-France-Hawai telescope for about 4 years, and then moved on to be actually the second astronomer hired at what was back then called the Gemini 8-meter telescope project, based in Tucson at the time. Spent about 4 years there, then came back to Hawaii with the Gemini construction team and led the instrumentation development program at Gemini for 5 or 6 years, and then eventually wound up being a director for Gemini Observatory. And then at the end of my term, as fate would have it, CFHT, Canada-France-Hawai telescope, was looking for a new director. So I moved one telescope over on the mountain, and for about 10 years was the executive director there. And then as fate would happen at the end of that term, the Institute for Astronomy was looking for a director. So I applied for that and landed this position as well, which I started last September. So Hawaii astronomy is my life's work, and it's been a real adventure, a real honor to have these sorts of leadership roles here in Hawaii, to work with students, the community. My wife is born and raised in Hawaii. We've raised our 3 kids here in Hilo. So we're very much connected here on the island to the university, to the community, and to astronomy. There are about a dozen observatories on Mauna Kea right now. I'll sort of mentally go around the ridge line. We'll start with Canada-France-Hawai telescope, which is kind of near and dear to my heart. That is a 3.6 meter optical infrared facility, specializes mostly in wide field imaging. They have an instrument called MegaCam, which at the time was the largest digital camera in the world at 340 million pixels. And they specialize in a variety of what we call large program surveys that are being conducted there. Next telescope over is Gemini, Gemini North. Its twin is in Chile on Cerro Pachon. It's an 8-meter telescope. Primarily its claim to fame, it's the most infrared sensitive telescope in the world. Between Mauna Kea, the advanced coatings that they used, it was really a challenge and fun to design that telescope to get what we call very low emissivity. They do a lot of what we call targets of opportunity research. So I think roughly a third of their research is based upon what happens to be going by right now, things that are in some transient state. So they fill a unique niche there. Next is the University of Hawaii 2.2 meter. That's the oldest telescope on Mauna Kea that UH owns and operates. Undergoing a major refurbishment now. It's about to have the first robotic adaptive optics system on Mauna Kea. So it'll be the 5th laser AO system on Mauna Kea, the most of any set of observatories in the world. It's also used for education and research for graduate students. So we move one telescope over, and that's the United Kingdom Infrared Telescope, which UH also owns and operates. And that is being used by the U.S. Naval Observatory to create a gigantic infrared survey of the universe. And that's part of what we call the Celestial Reference Frame development program. The Celestial Reference Frame is a spatial coordinate system ultimately tied to supermassive black holes and quasars that are used as a fiducial reference for a global positioning system. So your cell phone GPS is ultimately tied to the reference frame that's ultimately tied to here on Mauna Kea, the research being done. And then we go one over in Hokokea, which is a telescope, teaching telescope that's actually being relocated down to Halipahaka, the mid-level facility. That's the UH Hilo facility for students only. So it's a 0.7 meter commercially produced telescope. Then you go all the way down the mountain a bit and you get VLBA. That's a very large baseline array. That's actually not on the summit. It's about 11,000 feet up. It's part of a network of large radio telescopes all the way out to the Caribbean. I think there are 6 or 8 of them altogether. They work together to form an interferometer and jointly produce the highest resolution images of any ground-based observatory system in the world. It's really quite spectacular what they do. Hawaii is the western end of that whole chain of telescopes. Back up on the summit, we have Caltech Submillimeter Observatory. That's actually being decommissioned right now. We expect the first trucks to roll up in a few weeks to start to deconstruct that. That was about a 20-year project funded by the National Science Foundation, mostly focused on observing at what we call sub-millimeter wavelengths, very cold interstellar gas and dust. One telescope over from there is the James Clerk Maxwell telescope. It's a 15-meter monolithic telescope that is also designed and optimized for sub-millimeter research. Currently operated by East Asian Observatory. It's owned by the University of Hawaii. So we head back up the mountain top and we get the Subaru Observatory. And they are, of course, based in Tokyo, but have a very large facility here right next door to us in Hilo. That is an amazing facility. They do everything from wide field imaging. They're about to get a $100 million, what we call prime focus spectrograph, capable of recording about 3,000 spectra at a time. One of the largest upgrades in the history of the observatories, Mauna Kea. They also have the largest digital focal plane, hypersuprime cam, that's available. And then we move over to Keck Observatory, the Keck twins. They were established in the early and then mid-90s. The largest operating telescopes on Mauna Kea at 10 meters each. They work at optical and infrared. They have many claims to fame, some of which is, of course, the recent Nobel Prize research conducted there on the black hole in the center of our galaxy. And then one over from there, you have the NASA Infrared Telescope facility built and commissioned in the late 70s. And that is operated by NASA as a ground support facility. About half the time is used for planetary research, half for extra galactic research. And originally put in place to support the Voyager missions, as I recall, and Pioneer, in fact, I think prior to Voyager, and has a really incredible track record of performing solar system research for the past 40 years or so. It's been interesting to see the evolution of Mauna Kea astronomy over the course of my career. The number of telescopes have more than doubled since I was a graduate student here. And the international nature of the research and technical development is one of the most interesting aspects of the job. I think we have at least a dozen different countries that sponsor the facilities and the research on Mauna Kea. And that brings with it not just the cultural diversity, but the technical diversity and the scientific collaboration across lines that may not necessarily be politically as easy to mingle. For example, we have China and Taiwan both represented with access to facilities on Mauna Kea. The collaboration there is great. In the international world, it's a little more challenging between those countries. So it's nice to see how science can bridge where the political domains are more difficult sometimes. Overall, there's about 600 people that work on the Mauna Kea observatories. Roughly 60–70% of that are technical positions, so technicians and engineers. About 15% are administrative positions, and the other 15 is research. So astronomers like me are actually in the minority. When you look at how observatories operate, they're basically like a nonprofit small business. We have everything from procurement to human resources to accounting, to almost every form of engineering you can imagine, from laser engineering to electro-optics to mechanical, vacuum systems, etc. And then each observatory includes a host of research astronomers, either to perform the research on behalf of international astronomers that submit their proposals, or to host international astronomers that will come here and do their observations. One of the most interesting sort of forms of evolution has been the migration from the summit to the base facilities. When I was a graduate student, this was pre-internet, so we would haul our magnetic tapes up hundreds of pounds at a time and record on site with those tapes our data, and then bring them back to our institutes, and hopefully we get some good data. We wouldn't really know it at the time. Now everything is for the most part done remotely. In this building, we can remotely operate several telescopes at the same time, for example. Data comes down through extremely high bandwidth, 100 gigabit fiber links that we have in place now, and then gets immediately transferred to archives all over the world for immediate distribution to astronomers. So we've gone from physically hauling magnetic tapes across the world to instantaneous access, essentially, for data that comes off of Mauna Kea. And that allows us on essentially a daily basis to update and fine-tune observations as astronomers, say in France or in England or in China or wherever, will get data and then they can feed back into the system for the next night's observations if need be. So it's a complete revolution in how we can remotely operate these incredible facilities. That's been a real pleasure to watch. The technology involved in the instrumentation on Mauna Kea is really impressive in terms of how it has tapped expertise worldwide. My previous position at Gemini, which is to run the instrumentation program, gave me unique access ranging from teams in Australia to teams in the UK, be it London or Cambridge or Edinburgh at ATC, in Canada, Victoria, Montreal. We have teams in South America, and that gave me a real appreciation for how astronomy is so internationalized now. It really is a neat field in which we have achieved what we have through the bonds of collaboration, both technical and scientific. In my early days as an astronomer, it was much more siloed. In fact, some of the telescopes didn't really want to interact technically because there was competition maybe for the same money or something with a funding institution. But now we've cross-pollinated. There are no secrets left. I've worked at several facilities, many of us have, and it's kind of what we call a big ohana, or family, that has emerged over the years with the Mauna Kea observatories. Well, Jwst, having just come from the SBIE conference and seen an amazing set of results in person, is revolutionizing now the field of astronomy. One of the most amazing charts that I saw was the sensitivity of that instrument. Some wavelengths for some applications is 100 to 1,000 times higher than anything we've ever had before. That's the kind of improvement that an astronomer might see once in their lifetime. So we're going to see things with that kind of quantum leap in performance that we simply didn't know was out there as Jwst looks deeper and deeper into the universe. The sensitivity is so high compared to anything we've ever had in astronomy that it would be surprising and of course very disappointing if we didn't discover things that we simply didn't know were there initially. I was blown away by the initial first image. I think it showed a galaxy at Z of over 8, so it's an astronomical term for distance. And that object would have taken many weeks of observing with Hubble Space Telescope, and they did that in a few hours of observing. To give you a sense of when they actually start to integrate really deep and probe much, much closer to the very first stars, the first galaxies that were formed, I'm not quite sure what to expect other than it's going to be a remarkable transformation of our understanding of the early universe, no question about it. I was also blown away by just the images of Jupiter that they showed. It's nearby. I think those are the first images ever from Earth in which you can see the ring of Jupiter. The other observations have all been by flyby satellites. Voyager, I think, was the first interplanetary probe to image the rings. So you're going to see a certain amount of research that you can do from Webb that historically has actually been done by interstellar probes in ways that were simply unimaginable not that long ago. There's so many different things going on in astronomy right now that Webb could impact. For me, it's what we call new physics that I'm kind of most intrigued by. Because when we start to break through the understanding that we've had in place with quantum mechanics and general relativity, which have been the pillars for over a century, I, like many astronomers and physicists, I'm looking for the next pillar, so to speak, to transform our understanding of the universe. And regions like black holes are extreme regions in the universe where you probe and test these fundamental theories to their limits and see when and where they break. And maybe Webb will be able to help us do that, given its exquisite sensitivity. You need computational resources and things like AI and machine learning to be able to keep up with it. So we're pushing the frontier at data rates that are way higher than Webb. Haven't done it yet, but Webb seems actually fairly tame compared to these other huge ground-based projects, which are going to generate data at rates that are orders of magnitude higher than Webb. AI applications of huge databases. You see this sort of revolution in supercomputer technology, AI, and gigantic databases that were simply inconceivable not long ago. And to your previous question, you don't quite know what's going to come out of that because that type of research application has never been attempted before. And that's the exciting bit. We're going to learn something interesting. I'm just not quite sure what from this incredible amount of research going on. One of the most sort of profound and deep connections we have here at UH with Jwst is the development of the detectors in Webb. Almost all of them are what are called H2RGs. H stands for Hawaii. And UH has a long history of developing with initially Rockwell and now it's Teledyne, the infrared array sensors that are used worldwide and in space. In fact, just down the hallway here in this building is where the H4RGs, this is the latest incarnation of that technology, has been advanced. So it's a real thrill to think that the University of Hawaii, through about 30 years or so of infrared array technology development, working with commercial companies, has been able to enable that fundamental contribution to the most amazing observatory ever built, the sensors that actually collect the infrared light, read it out, and process it and then transmit it, have it transmitted back to Earth. I got my start as a grad student working with some of the very first infrared arrays. They were 32 by 32 pixels, which seemed amazing at the time because before that it was 1 by 1 pixel. So, big leap, but now these things are, at this point they're 4 by 4K detectors. They're about $1 million a piece, and the space flight versions are even more advanced and capable and expensive than that. So research-wise, we've got a lot of people on the IFA faculty that are involved in a variety of research. One of them, Klaus Hodap, who's just across the hallway here, is a member of the infrared camera team. So he has guaranteed access to Webb. And his specialty is looking at star formation regions at infrared wavelengths to sort of penetrate through the dust, the cocoon around these forming stars, and observe them in exquisitely high detail and contrast. And I know Klaus is very excited after working on Webb for, I bet you 20 years now, to finally have access to that incredible observatory to conduct his research. I spend quite a bit of time, and it's the funnest part of my job, interacting with students and the local community. The observatories have a multitude of programs for the local students in particular. Amongst my favorite is sort of the signature program. It's called Maunakea Scholars, in which we provide to local high school students, we've got about a dozen public schools in the program now, access to the observatories on Mauna Kea and Haleakala. And to my knowledge, this is completely unique. I refer to as a $1 billion sandbox for these high school students to explore in. They're mentored by most of the UH Infrared for Astronomy, Institute for Astronomy graduate program. And they help them prepare their proposals. I and a team review them like we would professional proposals, and then they're assigned observing time. We've had upwards of 1,000 students in the program so far, and it's been a thrill to see the transformation that program has on these young students. Also at the IFA, we're in the process of taking on board the Akamai internship program. Akamai, which is Hawaiian for wisdom and knowledge, is a college intern program for local college students. They can go to college elsewhere, but as long as their residency is here in Hawaii, they can qualify for it. And that's an incredible program, over 20 years now long. Most of the internships are provided by the observatories, quite a few by aerospace companies over on Maui as well. And we have something like 150 Akamai interns that are now employed in engineering firms and STEM fields here in Hawaii, and over 400 total if you include those on the mainland too. So for me, in this part of my career, the opportunity to give back, to prepare the next generation, to enable them through the Institute for Astronomy, to get them into the program, into the workforce development program that we've got, and ultimately into jobs here. I'm all about research and cool things like that, but my heart is actually tied more to the local kids, and seeing that they have the opportunities I had when I was a student. Seems like a long time ago at the university to eventually give them the keys to these facilities and use them in future generations. So that's important to me.